Section 413 is called no load operation and saturation curve. Now, up to this point, we've thought about how a DC generator works, and we're using this as the foundation for all of our electric machines in terms of understanding how they operate. But normally, when we increase the excitation current, the excitation current being the current that we supply to the coils that create the field poles, which create the flux that we rotate the coils through to develop a voltage. But, in theory, we should be able to increase that excitation current to whatever level and get a proportionate increase in the output voltage. Well, we're going to see, and this is very important to understanding, designs of electrical machines and their limitations. We're going to see that at some point, increasing the excitation current does not increase to any significant degree the output voltage. And the reason for that is this ferromagnetic material that these poles are made of becomes saturated, and it just can't accept additional magnetic flux. And all this is, due to the internal structure of these materials, and we'll go into a little bit of that, but primarily we need to understand that and understand that the design of a machine incorporates this, what we're going to call a saturation curve, into its construction. So let's look at that into some detail. Here is figure 418, and you can see the title of it is Flux per Pole versus Exciting Current. So what we have on the x-axis is excitation current that we supply to create magnetic flux. And what we see, and when we first started talking about per unit in chapter 1, I told you that we would see that more and more the further we go into the text. Well, here it is, right? This is flux per unit, and not making this video about that in and of itself. Just know that the reason that we're doing this, it gives us this look. We get to see things, not at a specific level, but more of a general sort of overview. So we're seeing this per unit usage here in this particular graph. But anyway, so what we have is increase our excitation current on the x-axis, and on the y-axis, we're seeing the associated flux with that excitation current. And so what we're noticing as we go through this thing is, from certain points on this curve, if we plot this flux here on the curve, we see that from, say, point 0 to approximately point A, that output flux is almost a linear response to the excitation current. And if we thought back to, linear relationships, we have our classic equation for that, the y equals mx plus b equation. And, that's pretty much what this section of the curve looks like right here, right? That's almost linear. Okay, so as I continue to increase the excitation current, as I reach this point, and we see that the linear portion of the curve ceases to be at that point, and there's this what we call a knee of a curve where it starts to bend and starts to flatten out. So this point from here to here, it's a pretty good response to an increase in excitation current. As a matter of fact, we're going from 0 to 1 with a 1 per unit increase in the flux. Now, over a similar increase, say this is from 0 to 1 amp, and I get that response, but going from 1 amp to 2 amps, I only increase from 1 per unit to about halfway between 1 and 1.25, so that would be what, 1.125? So what we're seeing there is we're increasing the excitation current, but we're not getting the same linear increase in the voltage output. Now, a lot of considerations that we take into account in our design application and all for the electrical machine that we're working with. Okay, so, that's interesting in the fact that, we're looking at excitation current and resulting flux, but really for the electrical machines, we want to see not the flux, we want to see the effect of that flux. And where that comes into play would be from equation 4.1, where we're getting the voltage, armature voltage, that's based on equation 4.1. So if I say, of course, the Z number set, right? That's a number of conductors. I can't change that. And let's say that the speed is constant. So really, what I'm looking at is an altering of the amount of flux that we have, right? That's the only thing changing. Now, what I want to see, and if I were to take this idea and I want to graph it instead of excitation current versus flux, I want to graph it in terms of excitation current and output voltage. That is where equation 418b comes into play. And what's really neat about this is that it looks exactly like this general curve about flux per pole versus exciting current. We see the effects of that when we look at it in terms of voltage output. And the reason that looks like that is because of this equation again, right? And so what's changing, these two guys are constant, the flux is changing, and so the voltage output ends up being based entirely on this equation, and that's what we're looking at on the two graphs, okay? So here I am with excitation current again, and I'm going, say, from 0 to 1 amp, and I see that same sort of portion here that's almost linear. Then it starts to, this is the knee, right, where it starts to level off. And so electrical machines in general are designed so that they operate almost in that linear curve, that linear portion of the curve. That's where we want to design our electrical machine to operate. And why do we want to do that? Well, the reason we want to do that in that area is we're going to see that it has a huge determination on the efficiency of the machine, which is a primary consideration in electrical machines. So, we can see this direct correlation here between excitation current and rated voltage output, armature voltage. 0 to 1 amp gets me 120 volts out. So there's an expenditure, you might say, of 1 amp. And then going from 1 amp to 2 amps, I go from 120 volts to the difference between 120 and 150. So what's the difference? 30 add 15 volts. So I would be at 135 volts for the next input of 1 amp of excitation current. Well, what we're going to find out, there's an energy cost to provide that excitation current. And, it's not very efficient to add another amp to only get 15 volts return, you might think. Okay, so the efficiency of that is not worth, so to speak, the investment of the additional amp of excitation current. So when I'm operating my generator, I want to run it here. This is where I determine the rated voltage of the machine. Okay, and then, he goes on to say, finally, if we were to reverse the direction of the rotation of the generator. The polarity of the induced voltages would also reverse. And if we reverse both the excitation current and the direction of the rotation, the polarity of the induced voltage would remain the same. We'll get to that specific detail a little bit later when we get into some other things, but that's just another sort of thought to go through, and just sort of take that for what it is at this point. All right, so that's 413, no load operation, saturation curve, and then equating that saturation curve to an actual output voltage.